Alrighty, good afternoon. Just looking into what we were arriving at from last time. Again, we have in working with functions and function values as well as functional expressions. Okay, and reverting back to what we have on page 147, and we have looking at the determination of function values. Again, we have with the notation. Okay, we have f of x, and again, this is another way of saying y, which is set equal to x squared plus 3x. And now we have for this particular function, okay, now this one is going to be comprised of an infinite number of points. And one of the points we have at x is equal to 5. And in terms of finding out what the corresponding y value is going to become, okay, so we have f of x is equal to x squared plus 3x, and change the input from x to 5. Okay, so we have operationally, okay, we're going to have f of 5 is equal to the square of 5 plus 3 times 5. Five squared is 25. 3 times 5 is 15. And we have that 25 plus 15 is equal to 40. Okay, so we have among the points on the graph of y is equal to f of x is equal to x squared plus 3x, we have 5, 40. Now for the next function, okay, it may very well be that number 47 is going to be virtually the easiest problem we have in the whole book. Now we have given g of x is equal to 1 over x. Okay, we're now looking at in number 47. We have g of t, and g of t corresponds to g of x, and guess what? We have g of the input is equal to 1 over the input. Well, guess what? The only change here is going from x to t, and here we have g of t is equal to 1 over t. So we have g of x is just going to be a reciprocal of the input function. And what we have to occur with t, okay, we're going to have the same thing to occur with x plus h for number 56. And now we're looking at g of x plus h. And again, just taking the reciprocal of the input, so you have g of x plus h is equal to 1 over x plus h. And we have now crossing over into looking at the domain of given functions. And we have fast forwarding onto number 100. Okay, and we have a change in the variables. Okay, so we have this time we have for part A, we're looking for the domain of y of t is equal to the square root of 16 minus t. And for what we have here in the setup, okay, now we have an even root function. And again, in the real number system, we cannot have an even root of expressions that are negative. Okay, so because we have a square root, okay, we have that 16 minus t cannot be negative. And setting up what we have as an inequality. Now we have 16 minus t. Okay, it can be positive, and it can also be equal to 0. So we have 16 minus t can be greater than or equal to 0. And from the inequality, looking at the determination of the values of t that will be allowed. And we have in the process, if we isolate the t term by subtracting 16 on both sides, so we're going to have negative t is greater than or equal to negative 16 And again, we are looking at finding out the solution or solution set for t. Okay, so right now I have negative t, and if I multiply or divide by -1, remember, if you're dealing with inequalities and you're multiplying or dividing by negative, you're going to change the direction of the inequality. So we have, this time around, okay, we have -1 times -t becomes less than or equal to -1 times -16. And so we're going to have that t is less than or equal to +16. And just looking at it from a visual approach, again, we have t is less than or equal to 16. So you have 16, and looking at, say, the graph of t is less than or equal to 16, so we have 16 thanks to the equal sign included. So we're going to have a solid point. Everything else will be less than 16, so there will be a ray going out to the left. And so the lower limit we have tending to -infinity. And looking at what we have for t is less than or equal to 16. Okay, so again, you have the inequality, you have the graph, and just looking at what we have with the interval notation, that's going to define the domain. Okay, so it is interval notation, and for what we have in the case of the domain, okay, so you have going from -infinity, approaching and including 16. Again, -infinity is balanced, so that stays in the parenthesis, and we have 16 is included, so that is going to be in the bracket. Now, in the case of what we have in part B, we have just a little bit of a change up. So we are going from y of t to w of t. And w of t we have expressed as another square root function, whereupon we have the square root of t minus 16. And we have much of the history to repeat in setting up what is going to define the domain of this particular function. Again, we have a square root radical, and just like 16 minus t moments ago, we cannot have t minus 16 to be negative either. And so we have, for t minus 16, again, it can be 0 and it can be positive. So for the setup, we have the inequality t minus 16 is greater than or equal to 0. And if we isolate what we have in t, so we have, upon adding 16 to both sides, so right away, upon adding, okay, so we're going to have t right away, which is going to be greater than or equal to 16. And so for t is greater than or equal to 16, again, we're going to have another solid point thanks to the equal sign. And this time around, instead of going to the left, okay, all the other values we have in t to be greater than 16. So there's going to be a ray that will be proceeding to the right. And we have tending to infinity. And again, infinity is boundless. And so we have with the domain. Okay, so we have, instead of arriving at and including, we are starting from and including 16. So 16 is in the bracket. And again, we have approaching positive infinity. Now, like negative infinity, infinity is boundless, so that remains in the parenthesis. Now, for what we have in the case of z of t, okay, so we have z of t. Okay, we have a bit of a twofold situation with the variable part of the right-hand side. Here we have the reciprocal of the square root of 16 minus t. So we have the appearance of the square root of 16 minus t from part A. Now we're looking at its reciprocal. And now we have, with the square root part, we have restricted that 16 minus t cannot be negative. And because we have 16 minus t in the denominator, the bottom part of a fraction cannot be 0. So not only is it that 16 minus t cannot be negative, it's also that 16 minus t cannot be 0. Okay, so it can't be 0, it can't be negative, so the only recourse is that 16 minus t has to be positive. And so we have here 16 minus t is greater than 0, and then isolating the t term. Once again, we have subtraction of 16 on both sides. So we're going to have negative t is greater than negative 16. And from part A, we have partial history to repeat. Again, if you change the sign values at both ends so as to convert from negative to positive t, again, we have the inequality direction to change from greater than to less than. So we're going to have that t is less than 16. And just looking at it from a visual approach. Okay, now, because we've been working with one number in each of the comparison inequalities, okay, there's a bit of a monotonous pattern, I know, with the graphing portion, but I just want to at least secure a foundation in terms of some of the other situations that will arise. And okay, so 16 is not included this time around, so instead of a solid point, as had been in the cases parts A and B, okay, we have, once again, 16 is excluded, indicated by the hole located, and again, to represent less than 16, so we have a ray that is going to go to the left, and the lower limit, again, we have at negative infinity. So we have, for the domain of this function, which would have to be simultaneously a rational expression and also radical expression, we have going from negative infinity, approaching but not including 16. So we have the exclusive use of parentheses for the interval notation. Now, for what we have in the case of the next item, and we have with 104, okay, I think I said look at 104 part C, but I think we'll look at all of these functions. And we have for part A, now we have a quadratic function with r of x, okay, and we have that is equal to x squared minus 4x minus 12. And there's nothing like an even root radical or a fraction Okay, and what we have in the x expressions, okay, we have in direct terms, okay, and there's nothing that disallows x from being, say, 0 or a negative or a positive. So we have, in this particular situation, okay, there are no restrictions on x. And because of this, okay, we have the domain is going to be the set of all real numbers. Okay, so if you were to graph, you would just have the whole number line. So you have going from negative out to positive infinity. And again, that is the interval notation for the set of all real numbers. Now we have, in the case of s of x, okay, so we have x squared minus 4x minus 12. And this time we have this to be all over x plus 1. Okay, now there's going to be a restriction for this particular function, and it's not going to come from the trinomial. Instead, it's going to come from the x plus 1. Again, we have for anything that is in the denominator of a fraction, and for the fraction to be a defined value. Okay, whatever's at the bottom cannot be equal to 0. Okay, so the restriction comes from x plus 1, since that is in the denominator position, and if x plus 1 cannot be 0, we have that x cannot be equal to negative 1. So that is going to be the restriction. And looking at what we have in terms of the domain, okay, so x cannot be negative 1. So negative 1 is excluded. Everything else is going to be included. Those values less than negative 1 as well as those that are greater than. So for what we have here, on the lower end as well as the upper end, okay, so you have excluding negative 1. So you have one specific exclusion from the domain. And so with each exclusion, you're going to have like an added subset to describe the domain in interval notation. So you have one exclusion, so there'll be two subsets. And so we have representing those values of x less than negative 1. We have, again, we have parentheses around negative infinity and negative 1. And then we're going to have this subset to be in union with the subset of values greater than negative 1. And that's going to be symbolized by parentheses around the negative 1 and the infinity. Now, in the case where we're going to have restrictions on this trinomial, this is going to arrive with t of x. Now, t of x is going to be the reciprocal or the multiplicative inverse of what we had for s of x. This time we have x plus 1 at the top and x squared minus 4x minus 12 on the bottom. And for what we have here, okay, now we have x squared minus 4x minus 12 is at the bottom of a fraction. Now before, it could be equal to 0 in r of x, and it could be equal to 0 in s of x. But because we have this layered at the bottom of a fraction, it can no longer be equal to 0. So with x squared minus 4x minus 12 disallowed from being 0, we also have it that the factors that form this trinomial cannot be equal to 0 either. So we have with the factors, we have the quantity of x plus 2 and the quantity of x minus 6, neither of which can be 0. So just taking what we have with the factors, okay, again, neither x plus 2 nor x minus 6 can be 0. If x plus 2 cannot be 0, we have that x cannot be equal to negative 2. And if x minus 6 cannot be 0, we have that x cannot be equal to 6. And just taking the graphing of the exclusions as a bit of a visual backdrop to the domain representation utilizing interval notation. Okay, so we have negative 2 excluded, so you have a hole or open circle on negative 2, and also for the same reason you have a hole on 6. And then we have in terms of the domain, so you're going to have 3 layers here. Okay, one is going to be where we have the set of values in x to be less than negative 2. And we have the middle layer, which is going to be the line segment connecting the holes situated on negative 2 and 6. And then we have for the top layer, okay, we have those values of x which will be greater than 6. So we'll have for the domain, okay, now sort of backtracking. Okay, so I had in part B, there was one exclusion that led to the development of 2 subintervals. Okay, so you have those dancing around the exclusion of negative 1. Now we have with 2 exclusions, we're going to have not 2 but 3 subintervals. Okay, and for this one, for the interval notation, so sort of dancing around negative 2, you'll have those values less than negative 2. And we have next in line, okay, we have those values greater than negative 2 and less than 6. Okay, so we had the values already having danced around negative 2. Now it's going to be already dancing around 6. So you have less than 6. And then for the final stretch, we have those values of x greater than 6. And we have indicated by the parentheses around 6 and infinity. So again, in the interval notation, this is what we will have for the domain. All right. Now, in looking at what we have going from functions in terms of the individual features, we're going back to looking at functional relations in the sense of the lead-in to equations in 2 variables. And again, the other day we looked into slope, and we have from page 162. Again, the other day we looked at the slope formula, and in the process, now we have for 28, we have 2 points given as negative 9, 4, and also negative 1, negative 6. And again, we have with the slope formula. We have y of 2 minus y of 1 all over x of 2 minus x of 1. And I know that from years past, okay, So I'm trying to go ahead and tackle the numbers before fully processing, okay, what numbers will represent what position in the formula. So as a bit of a visual guideline, okay, just almost like putting on blinders where this formula is concerned, keep in mind that all ordered pairs are of the form x and y. X is for the first coordinate, y is for the second. And if we go ahead and label what would be the first and second sets of x and y values there will be. So we have -9, 4, and we can say because this is given first, we'll let this be our x01 and y01. And since -1, -6 is given subsequently, let's say we have x02, y02. Okay, so you can go ahead and identify, okay, how you want to do your first and second sets of x and y values. If I had -1, -6 as x1, y1, -9, 4 as x02, y02, you're still going to get the same outcome. And now specifying just what the inputs will be. So for y02, again, that corresponds to -6. And we have subtracting. y01, we have it 4. For x02 minus x01, x02 we have at -1. We got subtracting x01. x01 we have at -9. Now for the change in the y values. Okay, so we have -6 minus 4, so that is a -10. For the change in x, we have -1 minus -9, so this would be a -1 plus 9. So you have -10 over 8. So for the slope, okay, this will end up as a negative ratio where we have -5/4. So for the slope of the line passing through these 2 points, again we have -5/4. So this would be like a process if you were to read incrementally from left to right. You'd be looking at going down 5 units and shifting over to the right 4 units. And we have, now for the next one, if you have a situation whereupon there are non-integer coordinates, and we have the next pairs, okay, we have this particular situation to arise. First point we have with the coordinates 3/4 and 6. Next one we have 5/2 and 1. And now if we just go ahead and identify what the x1, y1, x2, y2 will be. And again, just relegating what we have over into the slope formula. So we have a y02 minus y01. y02 we have at 1. And minus y01, so we have -6. x02 we have at 5/2. Minus x01. x01 we have at 3/4. So you have 1 minus 6. Okay, so this will be at -5. Now, in order to combine fractions, we've got 5/2 minus 3/4. 5/2, if I convert in terms of fourths, we have 10/4. And 10/4 minus 3/4. Okay, we're going to have 7/4 on the bottom. And here we have a complex fraction, not complex as in the square root of a negative or the letter I. But here we have like a ratio where we have a fraction in at least either the numerator or denominator. So here we have -5 divided by 7/4. And if I rewrite what I have in terms of multiplying, so if I divide by a fraction, it's going to be the same as multiplying by the fraction's reciprocal. So I'm going to remove 7/4 from the denominator position, flip it, and multiply -5. So we have -5 times 4 is -20, and we have over 7. So we have another negative slope, whereupon we will end up at -27. Okay, so exercises 28 and 33. Okay, they call for the use of the slope formula. Now, and what we have with number 39, you can still utilize the slope formula. Now, unlike 28 and 33, number 39 comes equipped with a graph. So you're going to have x-axis, y-axis, and for what we have in terms of the motion of this line, you have downward trend here as you move from left to right. And points through which the line is going to pass. Okay, so you have 0, 2. Now, so we have 3, 1. And again, you can use the slope formula. And you can have like a set of x01, y01, x02, y02 terms. Okay, when we say that 0, 2 will be x1, y1, 3, 1 will be x02, y2. But you could also do it where 3, 1 will be the first set, 0, 2 will be the second set. So we have with the slope. Okay, so here with y02 minus y01, you have 1 minus 2. For x02 minus x01, we have 3 minus 0. So 1 minus 2 is -1. 3 minus 0 is 3. So we have with the slope, okay, this will come out to -1/3. Also, I will mention this. You could also look at the graph from a triangular perspective, kind of like a little staircase pattern. So you would have here, so you have going down 1, and then also you have shifting over 3 units. So you're looking at the change in y with respect to the change in x. And from this particular vantage point, you still come out to the slope of -1/3. Now for number 42, okay, this time we have just a straight line running up and down, looks like. Okay, and at least from the way I read it, I don't know if this is a printing error or if it was just intended to be this way. But you have the line that's running between x equals 1 and x equals 2. And you can assign points in case you have like 1.5 or 3 halves. Let's see, we have 3 halves 2. We'll let this be x01, y01. Now we can say we have 3 halves 0. Will be the second set of x and y values. Again, just take what we have for the slope formula. So you have with y02 minus y01, okay, so you have 0 minus 2. And for x2 minus x1, guess what? We have 3 halves minus 3 halves. Change in y we have at negative 2. Now change in x, guess what? We have 3 halves minus 3 halves, which in this case comes out to 0, and because we have 0 on the bottom, okay, it turns out that the slope is going to be undefined. Again, anytime that the line is such that the slope is undefined, okay, you're going to have that the line is going to be vertical. Yes. All right. Now, with slope, okay, now there are formations of equations in 2 variables, okay, that will involve slope, and you're going to have, at least for the introductory cases, you're going to have a couple of formations that will be intertwined, okay, and the lead off, you're going to have the point slope form of a linear equation. Okay, now for the point slope form of a linear equation. Okay, now we're going to have the point slope equation of a line with slope m and that passes through a point again, we just label as x01, y01. It's going to be, and we have in the setup, now we normally say x before we do y, but in this case we're going to have the y expression out at the front. So we have y minus y01 is equal to the slope m, and we have times the quantity of x minus x of 1. Okay, so that's going to be the point slope equation. Now, in the case of the y that is jutted out of the front, isolating this y will lead to the formation of what is going to be the slope-intercept form of a linear equation. Okay, and for this particular expression, so you're spinning off items from the point slope equation, and so this same y here, we had to be isolated, and this is going to be set equal to mx plus b. Again, this is going to be where m is the slope still. And once you combine like your mx1 and your y1 terms, okay, you're going to have what is going to be the y-intercept. Okay, so m is the slope, and the y-intercept, again, whenever they talk about the slope-intercept form, the intercept part is going to be the y-intercept. So you have the y-intercept, you can say it's going to be in the form of 0b. Now the coordinate setup will be sort of like what the textbook prioritizes. And we have, with Alex, he likes to go with y is equal to b. So those are just two different ways of saying the exact same thing. Now, just examples of just how the point slope equation can lead up to the slope-intercept form of a linear equation. And let's say that if we have among the examples, okay, so if I were to determine the slope-intercept equation, and say we have given, first of all, okay, we can say that we have the slope is equal to 5, and that the point through which the line passes will be at -1, -2. Okay, so in the case of being able to work with the slope as well as the given point, okay, we will start out with the point slope algorithm. Again, so you have y minus y01 is equal to the slope m times the quantity of x minus x of 1. And we have substituting, so we have y minus y01 And the y1 we have at negative 2. So y minus negative 2 have equal to the slope m, which we have at 5. We have times the quantity of x minus x01, and the x01 we have at negative 1. And just undoing the notation regarding the subtraction of a negative. So we have y plus 2 is equal to 5 times the quantity of x plus 1 So for what we have here, and at least in this setup, okay, that is going to be the point slope equation. And to find out the slope-intercept equation, okay, we're going to be required, okay, to follow through and isolate y. So right now we have y plus 2, and we have with the distribution of 5 over the quantity of x plus 1, so we have 5x plus 5. And taking 2 away from both sides. So we're going to have that y is equal to 5x plus 3. Okay, so this is going to be the slope-intercept equation. And again, in the slope-intercept equation, whatever coefficient is alongside the x variable, that is going to be the slope. So the slope is equal to 5 once again. And for the y-intercept, now we have the b value at positive 3. So we have 0, 3, or y is equal to 3. Okay. And just sort of checking the consistency. Okay, so you had the slope at 5. Okay, that was provided. Okay, and if I were to test out negative 1, negative 2, so negative 2 for y, left-hand side becomes negative 2, and I want the right-hand side to be as well. So we have with x at negative 1, we got 5 times negative 1 is negative 5, negative 5 plus 3 is also negative 2. So this equation checks out for the slope and the given point that we had for x and y. Okay. Now, another situation here, and say if I have that the slope is equal to negative 4, and this time I had the point through which the line passes is going to be at 2, 6. Again, just looking at the point slope setup. So for y minus y01, okay, so we have y minus 6. And I have equal to negative 4 times the quantity of x minus 2. Okay. So this setup is also a point slope equation. And looking for the slope intercept, so I have y minus 6. And distributing negative 4 over the quantity of x minus 2. So I'm going to have negative 4x plus 8. And getting the y by itself. Okay, so we're going to add 6 to both sides. So we're going to have that y is equal to negative 4x plus 14. Okay. So this will also be the slope-intercept equation, and now we had the slope is at negative 4. And for the y-intercept, okay, so your b value is going to be at 14, so you have 0, 14. Again, another way of expressing the y-intercept, we have y is equal to 14. Okay, so we have the slope at negative 4, and we can test this out to see if 2, 6 is a point on the graph of this particular function. So with y at 6, left-hand side is going to be at 6, and I want the right-hand side to be as well. And so we have, with x at 2, negative 4 times 2 is negative 8. Negative 8 plus 14 is also at 6. And 6 is equal to 6. So we have consistency right there. Now, let's say that if you do not have the slope given, but instead have it that the line passes through 2 points. And we have to pass through 0, 6, and 2, 12. Okay, so we have in the setup. Now we don't have the slope given, so we have to utilize the ordered pairs we have here. So we have to revert back to the slope formula. And again, we can go ahead and label our first and second x and y values. And so for 0, 6, we have this to be representing x01, y01. And for 2, 12, I can have this as the second set of x and y terms. Okay, so looking at what we have for the change in y with respect to the change in x. So in y, we have 12 minus 6. And for x of 2 minus x of 1, we're going to have 2 minus 0. And 12 minus 6 is 6. So you have a vertical change of 6 with respect to a horizontal change of what is going to be 2 units. And breaking it down incrementally. Okay, so 6 over 2 is equal to 3, so you're looking at a vertical change of 3 units for every 1 horizontal unit shift. Alright, and now it is from the attainment of the slope that once we set things up in terms of the point slope equation, you can choose either of these ordered pairs to represent the x1, y1. So again, you can choose 0, 6 or 2, 12. Okay, in the point slope equation setup, okay. Again, it doesn't matter which one you have. Tell you what, we'll just go with 0, 6. Again, we have the slope at 3. Okay, so our x of 1 is going to be 0, y1 is going to be at 6, and again the slope is going to be at 3. If I substitute accordingly, okay, so y minus y1 becomes y minus 6. Then we have the slope m is going to be at 3. And we have times the quantity of x minus 0. Okay, so this will be our point slope equation. And then moving on to looking at the slope intercept. Okay, so we got y minus 6 is equal to, now x minus 0 is x, so the right hand side we're just going to have 3x. And getting the y term by itself. And we have upon adding 6 to both sides. And it's going to follow that for the slope-intercept equation. Okay, this is going to be at y is equal to 3x plus 6. And you can go back and check both of these ordered pairs. Okay, so again, we had the slope is at 3. And guess what? For the y-intercept, this was our first given point, which we had at 0, 6. So just looking at what we have now. So we have with 0, 6. So y is at 6 whenever x is at 0. 3 times 0 plus 6 is 6. 6 is equal to 6. And for 2, 12, y is at 12. So the left-hand side of this equation is at 12. Now for the right-hand side with x at 2, 3 times 2 is 6. 6 plus 6 is also 12. 12 is equal to 12. So this equation works for both of these ordered pairs. Okay. So the line represented by y is equal to 3x plus 6 does pass through both of these points. All right. Now, in looking at what we have regarding the slope-intercept form of a linear equation, and just going back to what we have on page 162. And for what we have in number 52, now we have a standard, or an almost standard form equation where we have x and y terms on the same side. And we have that 3x minus y is equal to 6. And the object is going to translate what we have here in terms of y equals mx plus b. So again, we want the slope-intercept form. Now for 3x minus y is equal to 6. If I get the y term by itself, so I can take 3x away from both sides. So here I'm going to have negative y is equal to negative 3x plus 6. And I want to solve for y. So what I can do here is I can either multiply or divide by negative 1. So if I do this, okay, what was negative becomes positive and vice versa. So we're going to have that y is equal to 3x minus 6. And so we have from this, okay, we're going to end up with the slope at 3. And for the y-intercept, Again, you have 0, -6 in coordinate terms, or as Alex might have it, we had that y is equal to -6. Okay, and again, just for the pattern here, for the slope equal to 3, so you're looking at, say if you're reading the graph in order from left to right, so be looking at going up 3 and out to the right 1, and just looking at the patterns. Again, so we have a y-intercept at 0, -6. Okay, and just for the trend here, so you got -1, 2, 3, 4. Okay, so we have 0, -6. If I go through the cycle, going up 3, right 1, I'm going up 3, and then to the right 1. Let's have another point. I'm going to do likewise, I have going up 3, and then to the right 1. I have yet another point. So I'm going from 0, 6, and then if I go to the right 1, so I'm going from x equals 0 to x equals 1. Now for y, going up 3 units. So I have -6 plus 3 is -3. And then doing likewise, shifting over to the right 1 unit. So I have 2. And then -3 plus 3 is 0. So I'm on the x-axis at 2, 0. And so for the line here, okay, so I'm going through these points among infinitely many others. Okay, so you have the trend up 3, right 1, up 3, right 1, and the up 3, again, adjusts the y value, and then the right 1 just increases the value of x 1 at a time. So you have, along with 0, -6, you have 1, -3, and 2, 0, also among infinitely many other points that will make up the graph of 3x minus y is equal to 6, which we have translated in slope-intercept form as y is equal to 3x minus 6. Okay, and we have also looking at converting, and we have with the layout in the case of what we have with number 62. So we have the coefficients in the form of fractions, whereupon we have x over 3 plus y over 4 is equal to 1. Okay, and let's say if I get out of the fractions, okay, now we're going to have in this setup, again, I want to express what I have in terms of y is equal to mx plus b. Now, for 3 and 4, smallest number that both 3 and 4 will go into will be 12. And if I multiply everything in the equation by 12, okay, so I have 12 times x over 3. And 3 will go into 12 4 times. Canceling out 4. 4 will go into 12 3 times. So we have in the rewrite, okay, so we have 4x plus 3y is equal to 12. And if I isolate the y term, first of all, upon subtracting 4x, we have that 3y is equal to negative 4x plus 12. And we have upon division by 3, okay, so 3y over 3 becomes y. We have y is equal to negative 4/3 of x plus 4. And so for this slope-intercept equation, so you have the slope is equal to negative 4/3. Notice we have a negative slope, so this would be along the pattern of going down 4 units while going out to the right 3 units. And with a constant 4, we're going to have the y-intercept, which is going to be 0, 4. Since b is represented by 4, or in the y is equal to b format, we have that y is equal to 4. Okay, so looking at what we have with the y-intercept, okay, so we have this as our starting point. Okay, so starting from 0, 4, okay, so the y-intercept is 0, 4. So if I were to start out, say, have going down 4 and to the right 3 units. Say going down 1, 2, 3, 4, over to the right 3 units. So I have a point on the x-axis. If I go down 4 units and then shift over to the right 3 units. And have another point. So we're going from 0, 4 to 3, 0, and then we'll have 6, negative 4. So again, y is going down 4 at a time, from 4, minus 4 to 0, minus 4 to negative 4, while x increases 3 units at a time. So we have 0 plus 3 is 3, 3 plus 3 is 6. And so for the line here, okay, this is going to be consisting of the combinations of the x and y values that will make up these points among infinitely many others, upon which x over 3 plus y over 4 is equal to 1, or y equals negative 4/3 x plus 4 is going to be represented. Okay, in terms of whether the top or bottom number is negative, it could technically be either one, but if you have a negative ratio, in most cases, you're going to read it as the top number being negative. It's kind of like, think of it like this. think of your y. Think of it kind of like the change in value of a commodity. So you have like X being time. You can have like January, February, March, April, May, June, and you might have the value of a commodity. Say if you say it might be at so many dollars per share or per ounce or whatever, and it's like if one is an investor and they see this trend line, okay, where you have going up in value, say going from 1 month to the next, they might be very happy and might be inclined to sell, okay, and just get out while the going is good. But if they notice this, that means that the value is going down. So wait a minute, the value is less in, say, the month of May than it was January, and if they put all their money into an investment, okay, that it's like so many dollars, and then all of a sudden the value drops where it's lower than it was to begin with, they wouldn't be too happy. But if there's like a sudden uptrend, you have a positive slope, and so they would be happy. Okay, so if you're looking at like positive change, negative change, like slope, like the positive and negative, normally you're going to read the graph in order from left to right. It's like January to February to March to April. So like the plus and the minus would be like in the case of the change in Y. So it could be both ways. Like if it were negative X, be like going back in time, but just like moving forward, like in time, like looking at present and future, you'll be looking at the negative applying to the Y. Right. And in the case of just a little mini lesson, we have, along with individual features regarding X and Y equations and the lines that are formed. And we have some relations between lines could be where they run either parallel or perpendicular. And I just mentioned, okay, so you have parallel lines. Parallel lines are going to be distinct lines that will have the exact same slope. And will never intersect. And just a quick case, okay, for what we have with parallel lines. We could say we have y is equal to 4/3 of x minus 2, and y is equal to 4/3 of x plus 7. Okay. So you have the same slope. M is equal to 4/3. And the lines are going to be parallel. And you can use shorthand like a sideways 11. Another case, you can have that y is equal to 7x minus 3. And y is equal to 7x plus 4. Again, both of these lines, you have slope is equal to 7, and the lines will thus be parallel. And just squeezing out the rest in case you have with perpendicular lines. Okay, you have meet at a 90-degree angle. And whose slopes will be opposite sine reciprocals. And what this is going to signal, if you have opposite sine reciprocals, so if you have with perpendicular lines, okay, you have like the product of the slopes will come out to -1. And I'll just kind of run through this. If I have like y is equal to 4/3 of x minus 2, the perpendicular line is going to have an opposite sine reciprocal, which you have going from a positive to a negative. The reciprocal we have going from 4/3 to 3/4, let's say x plus 7. And if I have y is equal to 7x minus 3, opposite sine reciprocal of 7 is going to be a -1/7. And a line such as -1/7 of x, we'll say plus 4, this will be indicating where we had the lines to be running perpendicular to each other. And just a shorthand notation for perpendicular will be an upside down T. Alright, and we'll let this be our stopping point.